Our next speaker is Dan Wallach. Dan is local. He's a professor of computer science and electrical engineering here at Rice. He's also a member of the Baker Institute for Public Policy. And Dan is well known for his work on electronic voting systems. And we're going to hear something about voting in his talk. Welcome, Dan.
Thank you very much. So why do we have a voting guy talking at a data privacy meeting? What does that have to do with anything? Well, voting is data, and we kind of want it to be private. And now we have an adversary, too. Because we're not just trying to protect the privacy of your bid, we're trying to protect the privacy of your vote, which is important to protecting your democracy. And even if we have great security, we've got great technology, we've got the NSA on our side, even then, fear, uncertainty, and doubt can have a tangible impact on the legitimacy of the outcome of an election. So today I'm going to talk a little bit about how we can bring science and technology to bear on the voting problem, and how some of that may be relevant to the broader data problem. I've spoken about this in a variety of different circumstances. This is me at September 2016, right before an election of some consequence that some of you might remember, testifying in Washington. This is the view you don't normally get on television, where you can see how many empty seats there are in Congress. But I want to rewind and tell you some security and privacy basics. So every security person starts with these three adjectives and then builds up from there. So what is confidentiality? We want to control who's allowed to learn a secret. Not everybody is allowed to know everything, as opposed to integrity, which is who's allowed to write or change a secret, or not even a secret. That might be a public value, but we want to prevent somebody from tampering with that value. And then availability, we want to make sure that the system is always there. We want to make sure that you're always capable of doing the thing that you're trying to do, whether it's bidding on an auction or voting in an election. Let's apply all this to voting now, because we're going to now get applied. Okay, well, confidentiality in voting means that your vote is private. Seems obvious, right? We want to make sure that who you vote for is not something that anybody other than you knows. And if not, then that clearly enables bribery and coercion. Bribery, vote for my guy, and I'll give you a bottle of booze. Coercion, vote for my guy, or you're fired. Either of these is completely legit in the threat model for elections. And that means that we need to engineer in mandatory privacy. We do not want voters to have the option to give up their privacy. So that's why people are unhappy about how come I'm not allowed to take a selfie in my ballot, because then you can sell your vote, and we don't want to allow that. The integrity is also important. We would like to have the vote tally at the end of the day to reflect what the voters put in the first place. Otherwise, what's the point? And that means we have to worry about ballot stuffing, damaged ballots, lost ballot boxes, all kinds of failure modes. And the paperless electronic voting systems that we vote on here in Houston are especially bad at this. Doesn't that make you feel great? They were really poorly engineered. You can drive a truck through the security holes. Yet we're voting on them. Yay. When you talk about availability of voting, now you're off in a very different world. Because now we have to worry about, what's the opposite of available voting? That's called disenfranchisement. These are techniques to prevent voters from voting. And, well, there's a long history of that, too, in this country and many others. If I can simply induce long lines, then I can cause voters to give up. I don't have 3 hours to stand in line. I've got to get my kid from daycare, etc. If I can systematically remove voters from the voter registration database, whether through legal or extra-legal means, that's a way that I can reduce their voting power. And God help us with online voter registration, which increasingly is a thing that we want in order to support vote centers. That way you can go to anywhere in the county and go to, whether it's the Fiesta or multi-purpose center, and anywhere you want to go, you can cast your vote. That's great. But that also means that there has to be a database to remember that you voted and you haven't voted. If those databases are online, and they kind of have to be, then we have to worry about them being attacked. And, oh, by the way, gerrymandering comes into play too. Because if I can redraw the lines, that's another way I can make your vote not count. More on that later. But let's start off with a simple, easy to analyze straw man voting system called voice voting. Now, I'm not making this up. This is how we used to vote in this country. This is a lovely painting from 1840, or depicting 1846, actually painted in 1850 or 51, of publicly voting in Missouri. First thing you might observe is they're all men, and they're all white, and you might say, as this fellow is casting his ballot, he's simply announcing it, and everybody hears it. Is that private? No. But it's got pretty good integrity, because everybody hears it. Now, okay, is this fellow trying to bribe or coerce people? Maybe. What's going on here? I'm not really sure, but he's having a good time. Is this an independent audit to make sure we're getting the correct outcome? Perhaps. Is this an informed electorate? I'm not really sure. But I think the point here is that when we have all the votes being public, auditing is easy. We have very strong integrity properties with this election. The problem is that we have no privacy properties at all, which means that this sort of voting is completely vulnerable to coercion and bribery, which was very much part of the concern at the time. And the solution at the time was called the Australian secret ballot, first rolled out in Tasmania in apparently 1856. It says it on Wikipedia, so it must be true. And it started appearing in the US in the 1880s. And it replaces, beforehand, the way most Americans voted was on what was called a party slate. So here are two ballots from Iowa. You can see in 1888, you showed up in the polls with a pre-filled ballot for your party. That's the party slate. So you'd have the Republican slate or the Democratic slate. And some people would actually scribble through and make changes. But nonetheless, you pre-filled your ballot. And you just walked in and dumped it in. But that also means that everybody could see who you voted for before you walked in. Whereas in an Australian secret ballot, you can see here from 1893, the state prints the ballot, or the county or the city or whatever, and then the voter marks the blank ballot. So it's a relatively recent design compared to the history of our democracy. So, modern paper ballots. If we look at those ballots from the 1800s, you might notice that they didn't have to answer too many questions. When you vote here in Houston, I think our last ballot had something to the tune of 80-something questions that we had to answer, right? It's terrible. You have to vote for all these judges, most of whom are running unopposed. Well, actually, this time they were running opposed, but that's not normal. You have to give all these opinions on all these things on which I'm sure you're all very well informed and you all carefully studied the voter guide, right? It took me 3 days to work my way through the Houston Chronicle's recommendations. Anyway, we have to count them by machine. There's no way you could efficiently and accurately do it by hand. Sorry. But do you trust the machines? What if the machines were programmed by that Putin character from the first slide? Well, turns out we have these cool things called dice. And they're cheap, and they come in all colors. And what you can do is a relatively recent technique, invented, I believe, by Philip Stark at UC Berkeley, and it's called a risk-limiting audit, and it's great. And the idea is that we're going to roll the dice, and that will give us ballot IDs, ballot serial numbers. And then those randomly selected ballots will go find the paper ballot, find the electronic scan, and they had better match up. And as long as we do that a couple dozen times, if they match up each time, we're good. And the trick that we're trying to prove with a degree of statistical confidence is that we have the correct winner of the election. Stark's analogy is, if you want to know whether your soup is too salty, you don't eat all the soup. You give it a good stir and you have a spoonful. And if that sample of the pot of soup has the right amount of salt, you know you're done. Same deal here, but rather than tasting soup, we're tasting ballots. And we're tasting them using dice. By the way, election officials love this because there's a tangible ceremony attached to standing around and rolling dice. So, I mean, don't discount that. It's important. And several states have either adopted it or are piloting it now. So this is like happening in many states. It's the future. But I'm going to change gears since I'm a computer guy and say I want to build a better computer voting system. Because of course I do. And we have plenty of examples of how not to build a good computer voting system. This is some press from the last two DefCon conferences, hacker conferences that happen every summer in Las Vegas. Because where would you rather go in August than Las Vegas? Yes, but it's a dry heat. Anyway, so the organizers of the voting village at DefCon used a sophisticated technology called eBay. And they purchased used voting machines, and they just stuck them in a room. And then hackery types walked in and said, "Ooh, toys," and broke them. All. Like, it's hardly even sporting. It's so easy to break these machines. So, great. We know that we don't trust computers. We like paper, right? But here's the problem with paper. We have to worry about the human beings marking that paper, right? So here's probably the most famous recent example. This is from a 2008 Senate race in Minnesota, the Franken versus Coleman race. And the election was really, really close. And then every ambiguous ballot, like the lizard people ballot, was litigated. And oh, by the way, if you want to have a good time, Minnesota Public Radio has a lovely website where they show you these images and they ask you to vote on what the ballot means. And then after you put in what you think, then they tell you what other Minnesota Public Radio voters think. There's a weird kind of Midwestern Minnesota humor tied into this that I can't quite put my finger on. But suffice to say that ambiguous voter marks are a real problem. And when you talk to election officials who have to manage paper, they say, "Ugh, that." Every election official says, "Ooh, lizard people, don't want lizard people." I'm not kidding. Okay, so how about machine printed ballots? This is a recent system put out by one of the top election vendors. Well, there's only really two, so it's also one of the bottom election vendors. And the way it works is that you press the touch screen, and when you're done, it prints on this piece of paper. And if we look up really close at that piece of paper, you have to ask, can voters read that microscopic type? You know, I recently joined the land of bifocal wearers, and now I can start to say, not so sure. And so we've got tiny fonts, and we've got barcodes, and who knows what the barcodes mean? And which is the one being tallied? Are we tallying the human-readable part, or are we tallying the machine-readable part? And what if they disagree? Who's going to notice? So this is not a terribly we've solved the lizard people problem, but now we've created this opacity problem. So how do we fix that? Well, in 2012, I and a whole bunch of other people gathered together in Austin, Travis County, our state's capital, and working with the Travis County Clerk's Office, we tried to design something better. So this is what happens when you lock a whole bunch of smart people in a room from completely disparate fields and tell them to solve the same problem. So first constraint, we want this was insisted upon by the county clerk, Dana de Beauvoir, who's fantastic. She said there must be a touchscreen user interface, not hand-marked paper, because lizard people. And this is also really great if you have low vision, if you have low motor control, if you have zero vision, if you are English as a second language, if you are illiterate. you name the particular issues. Voting is all about enfranchising all of the voters. And once you want to get all of the voters, now you have to deal with not everybody can do everything that you'd like. So a computer can have a button box, it can have headphones to read things to you, it can have large text for those of us who are losing our vision, etc. And unlike those earlier electronic voting machines, which, and I'm not making this up, cost like $3,000+ a piece. Anybody have a $3,000 laptop? Okay, one. We'll see if he still has it by the end of the day. There's no reason why we can't build a voting machine out of cheaper equipment. There's nothing about it's just a computer, and computers don't have to be that expensive. So if we can disentangle the hardware from the software, then we can buy off-the-shelf hardware and use custom software. Crazy idea, right? Has anybody ever heard of that business model before? It might have a future. But we're going to specify that there's a printer attached to the computer where we produce a paper ballot. And this is an early mock-up using this sophisticated technology called Microsoft Excel, where we could just put different things in different places. And in this mock-up, you will see that we only print the names of the candidates who are selected. And rather than that thing I showed you earlier, we're using an 8.5 by 14 US legal sheet, which means we can make the fonts nice and big and readable by us older people. And we're not having a whole lot of barcode going on here. We're assuming that a computer is capable of reading something that a computer printed using this sophisticated modern technology called optical character recognition. Crazy, right? Not really. Computers are actually really good at reading things that were printed by computers. The accuracy here will be fantastic. All right. I have one equation. Ready? So we're going to use a whole bunch of cool techniques that I'm not even going to begin to tell you how they really work. And one of those is something called end-to-end cryptography. So we want to have a crypto system that has a property called an additive homomorphism. That's super exciting. What that means is I can encrypt two numbers, and then I can take those two encrypted numbers and do this thing to them. We're calling it funny plus. And I can do a funny plus, and then it's as if I decrypted, added, and re-encrypted again. But I can do that without the decryption part. Okay, why is that a useful thing? Because that means that I can publish these things. And that means that anybody can look at them and anybody can do the funny plus operator. Anybody can add together millions of votes efficiently and compute an encrypted total. Now, only the election officials are going to be able to decrypt it, but they're going to provide a proof that they did the decryption correctly. More on that in a minute. But we do need a way for the voter to take home some kind of a receipt. And that receipt needs to protect their privacy, but it also needs to let them prove that that's their vote that was included in the tally. I'm really not going to explain how this one works, but it's super cool. They're called NIZKs, which stands for Non-Interactive Zero-Knowledge Proof. That sounds super like a mouthful. And all it is that I can have a proof that that thing that I encrypted is either a 0 or a 1. You can't tell if it's which one it is, but it's absolutely a 0 or a 1 and not something else. So that means anybody can look at all the encrypted ballots and make sure that the numbers that were encrypted are well formed. That I couldn't sneak in a ballot where I encrypt the number 1 million. That's a useful thing. I'm trying to prevent gross overvoting here. And once again, NIZKs are also used at the end of the day by election officials to prove that they did the decryption operation correctly. This is all like off-the-shelf stuff that cryptographers all understand. It's out of the toolbox of your favorite friendly cryptographer. A related thing is that earlier I said, oh, only the election official can decrypt it. What if you don't trust your election official? I don't trust my election official. So we can now take the role of election official and split it across a series of what are called trustees. So think chair of the Democratic Party for Harris County, chair of the Republican Party for Harris County, editor of the Houston Chronicle, editor of the Houston Press, lame professor at Rice. And we can take all of these and call them trustees. And now you pick any N for trustees and any K of N, So let's say there's 5 trustees, 3 out of 5 have to get together to do the decryption operation. If you don't have 3 out of 5, it ain't happening. That way, you don't have to worry that a single malicious election official can decrypt individual ballots and violate your privacy. So this coalition has to come together to do the work. And oh, by the way, when they're done, they produce a proof. I've been given a 5-minute warning. We also have a cool thing called hash chaining, which is similar to Bitcoin, except without the coin part. And the idea is that we can make sure that your vote wasn't tampered in transit. So you can find your vote later. And in fact, not only can you find your vote, you can make sure that votes earlier than you in the day weren't tampered. I'm going to skip over how we make sure the machine doesn't cheat. But trust me, if the machine tried to cheat, we would catch it in action with a signed confession that it cheated. Super cool. But the voter walks away with sort of a receipt-shaped thing, and that little QR code is really just the hash of their encrypted vote, so you can find it in that public bulletin board. We even built a prototype ballot box. That's the guts of an HP inkjet printer with the printer part removed, because the printer's inkjet sucks. But the actual thing that grabs the paper and pulls it in, very reliable. So we were able to build a ballot box prototype and get this thing kind of limping along. Will this ever show up in a real election, real voting? Talk to me later. It's complicated. Politics and money and stuff. But since I'm running low on time, I wanted to come back to this gerrymandering point, because I also want to protect the availability of elections. So the origin of the term was the 1812 governor of Massachusetts named Elbridge Gerry did that, and the Boston Gazette newspaper said it looks like a salamander. Gerry, salamander, gerrymander. Get it? All right. So this is the Texas congressional district map. And if we zoom in a little bit, so there's Travis County. Notice all the little colors weaving in and out of Travis County. So here's a zoom in, and what you should have, so I haven't updated this for 2018, but it looks basically the same. You might notice that Travis County's voters have a whole bunch of Republicans who represent them and 1 Democrat. And if you look at that, you say, but wait a minute, Austin, that's where all the liberals are, right? So, in fact, the Texas 35th, represented by Lloyd Doggett, in the 2018 election, you see he took 71% of the vote, not even close. But look at the shape of that. Look at the shape of the blue blob. It threads its way from Austin all the way down to San Antonio. So in gerrymandering lingo, this is a packed district. We're piling all the Democrats into a box such that, yeah, you get to elect a Democrat, but all the votes that you'd cast after that 50% plus 1 are all wasted. So 2016 House races, there was exactly 1 competitive race in the entire state of Texas for that district that's everything but El Paso. That's Bill Hurd. He won by a hair. Not a single Texas incumbent lost in 2016. 2018 was a little bit more interesting. This was a huge wave election, the best year for Democrats in forever. And I count 10 vaguely competitive races and only 2 flips. So this tells you the power of gerrymandering, that we can take a huge wave election, the greatest Democratic wave in decades, and it only flipped 2 seats. So here's the overall math in the current Texas Congressional Delegation. There are 13 Democrats, 23 Republicans, and 0 Libertarians. I've left the Greens off because so does everybody else. And compare the percentages of representation in the House versus what happened in the Senate race. So we all know it was a tight race between Beto and Ted. And if you look at those, you might think that Texas is actually pretty tightly matched between Democrats and Republicans. Well, but effectively 4 seats were lost due to gerrymandering. I've been told to hurry up, so I'll tell you that gerrymandering is just an algorithm. How does it work? It's like graph theory, and to a computer scientist, they're like, I can do that. The trick is, how do you know where to draw the lines? You have to know where the Democrats are and where the Republicans are at a pretty granular level. And it turns out every time you vote in a primary, you vote in the Democratic primary or the Republican primary, you're putting a giant light bulb over your house saying Democrat here, Republican here. So that data is public. The fact that who you voted for in the Democratic or Republican primary is private, but that you voted in as a D or an R is public. Local politicians will use the phrase that you're a triple D Democrat because you did it 3 primaries in a row. Anyway, so you also have your consumer data. You also have your neighbors' data because people tend to live around people like them. That's called homophily. And there was a famous piece in the New York Times a couple of years ago where they talked about how Target was able to infer women were pregnant because they bought hand lotion. Okay, but big data never lies, right? All right, so wrapping up, gerrymandering is an availability attack. And the reason why I wanted to come, and of course, are we going to fix gerrymandering? Yeah, work in progress. We'll get there eventually, I hope. But the thing I wanted to leave on that's relevant to today's symposium is that if we're talking about differential privacy, well, what would it mean to apply differential privacy to election results? What if we added noise? But could we do that in a way that still gave you confidence that we were producing the correct outcome? Could we add, if we have regulations to protect consumer privacy, would that as a side effect make it harder to do gerrymanders? If we can privatize the data that feeds into the gerrymander machine, maybe we can make gerrymanders less effective. And on that, thank you very much.
So I appreciated your bringing in the CIA part and not only looking at the disaster recovery, but the business part of it, making sure that a who was there to do it plus the machine. Did you have you thought about so those are basically security principles. Have you applied any privacy principles to that? Or maybe they don't quite fit, if that's a fair question.
So have we applied privacy principles to the engineering of voting machines? Well, to some extent, the fancy crypto that I gave you a very broad hand wave of is all about protecting voter privacy. The challenge is, so there's actually a really interesting tension between privacy and integrity. I can dial the knob all the way to integrity and give up privacy. And if I dial it all the way to privacy, do I give up integrity? So the crypto tricks get us partway into an interesting place in the middle. The statistical auditing tricks also give us some interesting power. And there's an active research community looking at new techniques that we can come up with.
What is the rationale or the basis upon which what primary I choose to vote in can be made public? I never really have understood that.
So why do we do things the way we do them here? I mean, every state's different. In many states, you must register as a member of the Democratic or Republican Party. In Houston, you don't have to register. Yay. Texas, really. But the fact that you chose to vote in that primary, the parties want to know. The parties want to know who their supporters are. And if you tried, I think it's completely in scope to say maybe we shouldn't. I think that's a completely rational thing to request, but you have to form the thought that that's maybe not a good idea. Then you can go to Austin and try to get them to change the law. Today, that's how it works.
This kind of goes back to the earlier issue, but cost versus reality versus political games, what does it take to change the system? Do all parties agree that there's a problem and willing to find the money to solve that problem?
Gosh, I have been playing in this space for almost 2 decades, and what I can tell you is that this isn't a partisan issue. What it is that whoever won is generally happy with the way they won. And it's the loser who requires convincing and who's unhappy with how they lost. So it's election integrity activists and researchers are always behind the 8 ball, because the people who you're trying to convince to change the system are the people who got there by virtue of how the system operates. So this is fundamentally a hard challenge. And it doesn't help that the vendors who sell voting equipment are terrible. Yeah.
Okay, let's thank Dan one more time. Thank you
you.
very much, Dan.